Bismillahirrahmanirrahim. Assalamu alaikum. My name is Thura Najaf and my roll number is 21TE06. Today I will be discussing the lab number 7 of digital signal processing, and the lab title is Frequency Analysis of Digital Sequences. The lab objectives are study digital sequences in terms of frequency spectrum, contribution of high frequencies in a sequence, contribution of low frequencies in a sequence. Task 1. Consider the following sequence. Plot the signal in MATLAB or Octave. If sampling frequency is 20K sampler per second, then part 1 is to redraw the sequence after removing the frequencies above 50K Hz and observe and discuss the effects of this removal of frequencies. Part 2 of this task is to redraw the sequence after removing frequencies above 70K and then observe and discuss the effects of this removal of frequencies. Here in MATLAB, we have defined the sequence X in an array, and fs is the sampling frequency. Now, to calculate the time vector, the t is calculated based on the length of the sequence x and the sampling frequency fx. For plotting, we see the original signal x is plotted against time. Both plot and stem functions are used for visualization, and the plot includes markers of each point with the symbol this and stem plot with red markers. Filter design for the 5 kHz cutoff. A low-pass Butterworth filter is designed with a cutoff frequency of 5 kHz, and the filter coefficients B and A are obtained using the Butter function. The filter order is set to 6, and the frequencies above 5 kHz are removed from the signal X using the filter function. For plotting the filtered signal after removing the frequencies above 5 kHz, we use the function plot and stem both to observe the graphs. Now, for the filter design for the 7 kHz cutoff frequency, we use another low-pass Butterworth filter, and this time we have the cutoff frequency of 7 kHz. The coefficients B and A are computed using the Butter function, and this is the filter with the same order. For plotting the filter after removing the frequencies above 7 kHz, we again use both the plot and the stem functions. Now, if we run the code, we observe 3 subplots. The first one is the original plot, the second one is for the signal after removing frequencies above 5 kHz, and the third subplot is for signal after removing frequencies above 7 kHz. The blue line shows the signal from the plot function, and the red line shows the plot using the stem function. Task number 2. In this task, we have been given an audio sequence, and we have been asked to perform 3 different tasks on this audio sequence. So I will be performing this task in 3 different categories. The task 1 is to calculate the DFT. Here the audio signal music.wave is read by the function audio read, and the audio signal y and the sampling frequency fs are obtained. Audio playback, the original audio y is played back using the sound function with a specified sampling frequency of fs. Now for the discrete Fourier transform computation. For this, the audio signal y is computed using the FFT function, resulting in the DFT coefficients stored in the variable DFT. For the removal of the upper frequencies, the upper half of the frequencies in the DFT coefficients, which correspond to the frequencies above the Nyquist frequency, are set to 0. And this effectively removes any frequency components above the Nyquist frequency to avoid aliasing during reconstruction. For frequency vector calculation, a frequency vector f is computed using the length phase function to represent the frequency range from 0 Hz to the Nyquist frequency, which is fs divided by 2, which is a sampling frequency divided by 2, with a length corresponding to half of the length of the DFT coefficients. This frequency vector is used for plotting the magnitude spectrum. For the magnitude spectrum plotting, in the first subplot, the figure, the magnitude spectrum of the audio signal is plotted against the frequency f, and the magnitude of the DFT coefficients within the valid frequency range is plotted in the ABS function. For the signal plotting of the original audio, it is done in the second subplot. The original audio signal y is plotted against time, and the x-axis represents the time in seconds, and the y-axis represents the magnitude or amplitude of the audio signal. Now, if we run the code, here we see in the first subplot, the magnitude spectrum of the audio signal is plotted against the frequency f, and in the second subplot, the original audio y is plotted against time. In part 2, we have been asked to remove the upper half of frequencies, that are the frequencies above fs by 4, and observe the changes by listening to the audio. So here in the MATLAB code, the music file or the audio file music.wave is read using the audio read function, and the audio signal y and the sampling frequency fs are obtained from the file. The length of the audio signal y is stored in the variable n, and the discrete Fourier transform of the audio signal y is computed using the FFT function, which is then stored in the variable dft. For the frequency domain modification, an index is calculated which corresponds to approximately 1/4 of the length of the index signal. All DFT coefficients beyond this index are set to 0. Then this effectively removes the higher frequency components from the audio signal in the frequency domain, retaining only the lower frequency components. For the inverse Fourier transform, the modified DFT coefficients are transformed back to the time domain using the inverse Fourier transformed via the IFFT function, and the resulting time domain signal is stored in the variable modified signal. For the audio playback of the modified signal, the modified signal is played back using the sound function here. So now when we run the code, here we see that the upper frequencies of that are greater than fs by 4 are removed. In part number 3, we have been asked to remove the lower half of frequencies, that are the frequencies below fs by 4, and observe the changes by listening the audio. So here in observing the MATLAB code, the code will be same as per the previous code. The only change that will be done is here in this part, where the coefficients from the beginning up to the index calculated are set to 0. So when we run the code, here we observe that the lower half of the frequencies that are lower than fs by 4 are removed. That's it from lab number 7. See you in the next video.